Lesson 931. Now we turn our attention to hypothesis tests for population means. In earlier lessons, we learned that there are two basic forms of statistical inference: confidence intervals and hypothesis tests. In earlier lessons, we constructed confidence intervals for a population mean. Now we will test the hypothesis that a population mean is equal to a specified value. We use the four-step hypothesis testing process that we've seen in earlier lessons. Monarch's magnetic fields. Some people believe that the Earth's magnetic field guides some animals as they travel over great distances. However, it is not clear how these animals detect the Earth's magnetic field. The monarch butterfly is an example of an animal that may travel this way. Monarch butterflies cannot survive a long cold winter, so they migrate long distances south in the fall. Monarch butterflies fly to the same winter roosts year after year. Often they fly to the same trees each winter. It is not known how the monarch butterflies locate their winter homes. One possibility is that they have some magnetic material in their bodies that allows them to sense a magnetic field. Biologists wanted to determine whether monarch butterflies have some magnetic material in their bodies. The biologists used a tool called a magnetometer for this test. The magnetometer measures electromagnetic units that are called nanoemus. Unfortunately, the magnetometer itself creates some magnetic intensity. The magnetometer creates about 20 nanoemus of magnetic intensity. A nanoemu is 10 to the negative 9 electromagnetic units. In order to demonstrate the monarch butterflies have some magnetic material in their bodies, the biologists needed to be able to show that the monarch butterfly's mean magnetic intensity is greater than 20 nanoemus. For this test, we will use a 5% level of significance. We will assume that the population of magnetic intensities in monarch butterflies is normally distributed. So step 1 in our hypothesis test, we first have to determine the hypotheses. As we've seen before, the null hypothesis states that the population mean is equal to a specified value. So again, the null hypothesis always involves equality, and in this case we are using population mean as our parameter, and we are setting that equal to a specified value. So mu for population mean is equal to some number k, which is just a constant, some number. The alternative hypothesis then involves an inequality, again relating the population mean to that number k. So either mu is less than k for a left-tailed test, mu is greater than k for a right-tailed test, or mu is not equal to k for a two-tailed test. Number 1, let mu be the mean magnetic intensity for all monarch butterflies. Part A, state the null and alternative hypotheses. So first of all, an easy thing for where we are here is H sub 0 always stands for the null hypothesis. Then what that hypothesis says, we write after a colon. We use the symbol mu for population mean, and then we are going to use the equal sign. And now all we need is just from our example, what is that number for the mean? If we go back to what was given, we'll see that in order to demonstrate that monarch butterflies have some magnetic material in their bodies, the biologists needed to be able to show that the monarch butterfly's mean magnetic intensity is greater than 20 nanoemus. So we are comparing the mean magnetic intensity to 20. That becomes the constant that we're using in our hypotheses. So the null hypothesis would be that the mean is equal to 20 nanoemus, and the alternative, HA colon mu, they are trying to show that the magnetic intensity is greater than 20, so we would use greater than 20. And then part B, is this a left-tailed, right-tailed, or two-tailed test? It is right-tailed, and that is because we use the word greater than in the description, and we also use the greater than symbol in our alternative hypothesis. After we've stated our hypotheses, then we move on to collecting the data. Step 2, or number 2. The biologists examined a random sample of 16 monarch butterflies. The measured magnetic intensity in nanoemus of each monarch butterfly is given in the table below. So here we have the magnetic intensity of monarch butterflies, all measured in nanoemus. And we have all 16 of them listed in those 2 rows. So first of all, part A are the criteria for approximate normality of the sampling distribution of sample mean satisfied. So one part of the criteria is n greater than 30. N stands for sample size, and we were told that our random sample only has 16 monarch butterflies, so that would be no. But we also have the other part of the condition is, or the population is normally distributed. And we do have that because the population is normally distributed was under assumption. So we do have the criteria for approximate normality satisfied. And that's by assumption. It's important to note that you only need one of those things to be true. Part B, calculate the sample size, sample mean, and sample standard deviation. So think back to how we have done this over the last few lessons. We're going to make a list and then use one variable, statistics. Sample size is n. We already know that that's 16. Sample mean will be x bar, and sample standard deviation will be s. So let's just take a minute and figure out what that sample mean and sample standard deviation are. So what you should get for the sample mean is x bar equal to 28.981, and then your sample standard deviation should be 14.150. Part C. Is the sample mean consistent with the alternative hypothesis? This means, if you go back to our alternative hypothesis, that stated that the mean should be greater than 20. So really this is asking, is the sample mean greater than 20? And the answer is yes, because our sample mean, 28.981, is greater than 20. Step 3, assess the evidence. In this step, we calculate the test statistic and the p-value. The test statistic varies according to a t-distribution when 2 criteria are met. First, the sampling distribution of sample means is normal, and we use a sample standard deviation to standardize the sample mean. The formula for the test statistic is the same as what we've seen before. Capital T equal to x bar minus mu divided by the fraction s over the square root of n. We will use technology or tables to find p-values. As before, we are going to use the TI-84. So first, just a little bit of a review of these p-values. Remember, for a left-tailed test, the p-value is the area to the left of the test statistic. So that is the p-value here. For a right-tailed test, like the one that we are conducting right now, the p-value is the area to the right of the test statistic. Also, these markers here, those are your test statistics. And then for a two-tailed test, the p-value is twice the area to the right of a positive test statistic or twice the area to the left of a negative test statistic. So you would only have one of those and then calculate the area beyond it. Number 3, we can use the t-distribution in this case since the normality criteria for the sampling distribution are met. Part A, calculate the test statistic for the observed sample mean. So this means t equal to x bar minus mu divided by the fraction s over the square root of n, which means we have in the numerator 28.981 minus 20, and then in the denominator we have the fraction 14.150 divided by the square root of 16. Notice how I'm using parentheses here. This way, if you're trying to use your calculator all at once, you want to make sure that you're typing it in that way. So 28.981 minus 20, and then divide parentheses 14.150 divided by the square root of 16. And you should get for that approximately 2.539. So that becomes our test statistic. So if you think of the graph that we have just above this for our right-tailed test, that is that TS, the test statistic. Part B, sketch the t-distribution and identify the position of the observed test statistic. Shade the area that represents the p-value. This is just like that picture that we have up above. It's something that looks like a normal distribution. Our t-statistic is on the right because it's positive, so that's 2.539. And then the shaded area for the p-value, that's the area to the right. Part C. Is the test statistic unusual? Please be sure to explain your answer. Think back to z-scores. Remember that usual z-scores were between -2 and 2, and unusual z-scores were scores that were beyond that. So ones that were less than -2 or greater than +2. It's similar with the t-distribution. Think back to when we compared those two distributions. So we would say yes, because the test statistic is greater than 2. And finally, part D. Use the test statistic to find the p-value. So this is going to involve a new function, and there's a couple of ways that we can do this. One is very familiar with the normal CDF method. So you can choose second, vars, and then look for tCDF. And then you are going to put your numbers in as, again, a lower and an upper score. So you're going to have lower t-score, comma, upper t-score. If you're on the TI-83, it would be just like this. If you're on the 84, they actually have the words lower and upper there. And then you do need one more number, DF, which remember stands for degrees of freedom. So you would enter those in exactly like I have, tCDF, and then 2.539 is our lower because this is a right-tailed test. The upper would be 1E99, and then your degrees of freedom would be 16, your sample size, minus 1, which is 15. And then if you calculate that, you should get approximately 0.011. There is another way that we can do this. The other way that you can do this is if you push the stat button, and then go to tests and choose t-test. And I'll show you what that looks like on a calculator. So I'll press the stats button, go over to tests, and then down to t-test. And you can see what we have here is a way to input our data or just our stats. So since we've already calculated our stats, I'm going to put all of these numbers in. So first of all, This first number says mu sub 0. This is the number that comes from your hypotheses. So I have 20 entered in here. And then x bar, that's the sample mean that we already found, 28.981. And then sx, which is 14.15, that was our sample standard deviation. N, our sample size is 16. And then you have to choose which symbol you used in your alternative hypothesis. We used the greater than symbol. And then I'm just going to go down to calculate and press enter. And so now you can see everything that we actually got before this, like our t-score, 2.539. That's what we had as our t statistic. And now you notice the letter P right there, 0.011, which is the same answer that I had from using the t-CDF. So now that we have our p-value, we'll go on to step 4, stating a conclusion. Number 4, do the data provide enough evidence to claim that at the 5% significance level, the mean magnetic intensity for monarch butterflies is greater than 20 nanoemus? So first of all, part A, how does the p-value compare to the significance level? So our p-value is 0.011, which is less than our significance level alpha, which if it's 5%, that's 0.05. So because we have our p-value is less than alpha, that less than, meaning p-value is less than alpha, that's telling us to reject the null hypothesis. So then part B, what can you conclude about the alternative hypothesis? If we reject the null hypothesis, this means our data supports the alternative hypothesis. And then finally, part C. State a conclusion in the context of the problem. Be sure to explain what the conclusion means in relation to the magnetic intensity of monarch butterflies. So if we think about our alternative hypothesis, the data supports that. And if we go back to our hypotheses, our alternative hypothesis is also the same thing as the claim, because the claim in the paragraph above, our hypotheses said, we want to be able to show that the mean magnetic intensity is greater than 20 nanoemus. So if the data supports the alternative hypothesis, then the data supports the claim. And we need a complete sentence here. We need to state in context what was the claim. So the claim was that the monarch butterflies mean magnetic intensity is greater than 20 nanoemus. Also, the secret word for this lesson is butterflies. So next steps, another example. Mean lifespan of batteries. Imagine that a company sells portable walkie-talkie radios to construction crews. The batteries for these radios last for an average of 55 hours. The purchasing manager for this company receives a brochure in the mail that advertises a new brand of batteries. This new brand of batteries is cheaper than the brand that the company currently uses. However, the purchasing manager is concerned that the cheaper batteries may have a shorter average battery life than the current brand. Note the number of hours that batteries last is called their battery life. The pricing manager wants to perform a statistical test at the 1% level of significance to determine whether the cheaper batteries have a shorter average battery life. So, first, step 1, state the null and alternative hypotheses for this test. So just like before, Our null hypothesis is going to involve mu equal to a number, and our alternative hypothesis will involve mu somehow unequal to a number. So we need to figure out just what that number is and what will be the inequality sign for the alternative hypothesis. Going back to what was given, we can see that the manager wanted to perform a statistical test to determine whether the cheaper batteries have a shorter average battery life. And what he is comparing this to is what he already has for those batteries. The batteries for the ones that are already being used have an average lifespan of 55 hours. So 55 is the number that we are comparing the mean to. And if it's shorter than, that would be less than for the alternative hypothesis. And then number 6, is this a left-tailed, right-tailed, or two-tailed test? This is left-tailed because there is a less than symbol. Step 2, collect the data. To test this hypothesis, the pricing manager installs 40 randomly selected batteries of the new brand in the company's walkie-talkie radios. He finds that the mean lifetime for the sample is 52 hours, with a standard deviation of 10 hours. Number 7, does the manager's sample satisfy the criteria for approximate normality of the sampling distribution of sample means? So, do we have n greater than 30? Remember, n stands for sample size. We have a sample of 40, so we would say yes. And then number 8, is the sample mean consistent with the alternative hypothesis? So if his sample mean is 52 hours, that is less than 55. So yes, that is less than 55, so that does agree with the alternative hypothesis. Number 9, calculate the test statistic for the observed sample mean. So here we were already given what the sample mean and sample standard deviation were. So putting that all together, sample mean 52 minus assumed population mean 55 divided by the sample standard deviation 10 divided by the square root of sample size, which is 40, and that would give us approximately negative 1.898. We get a negative t-score because our sample mean is below the assumed population mean. Number 10, sketch the t-distribution and identify the position of the observed test statistic. Shade the area that represents the p-value. This time we have a test statistic that's on the left, negative 1.898. And since we have a left-tailed test, the p-value is the area to the left. And now we're going to calculate that p-value. So this time, when we're using TCDF, we still need to put on our lower t-score and our upper t-score, and then our degrees of freedom. But since we have a left-tail test, the lower t-score is negative 1E99. The upper t-score is negative 1.898, and the degrees of freedom would be 40 minus 1, which is 39. If you use the t-test, you would just enter in the sample mean that we have up above, the sample standard deviation, the assumed population mean, and then you would find out what the t-score and p-value is all from that. And you should get that the p-value is approximately 0.033. So then number 12, how does the p-value compare to the significance level? So our p-value is 0.033. Our significance level was 1%. So this is greater than alpha, which is 0.01. That's 1% as a decimal. So since we have our p-value greater than alpha, this tells us that we fail to reject the null hypothesis. So if we fail to reject the null hypothesis, this means that our data does not support the alternative hypothesis. So notice with these two examples we've seen, if you reject the null hypothesis, that means the data does support the alternative hypothesis. On the other hand, in this example, if you fail to reject the null hypothesis, that means the data does not support the alternative hypothesis. So then number 14, state a conclusion in the context of the problem. So again, if we go back to our hypotheses, then we can see that the test that the manager was conducting was seeing if the batteries had a shorter average battery life. This was the alternative hypothesis. So this is our claim. Or we can also say that the data does not support that the batteries have a shorter average battery life. So we can either use the words of claim, or we could just state something about the battery life. So we can say at a 1% level of significance, we cannot conclude that the average lifespan or the average battery life of the new batteries is less than 55 hours. And then finally, a little bit of some review of an earlier concept. Number 15, it is possible that the conclusion that we just got was incorrect. The new, cheaper batteries may indeed have a shorter lifespan than the old batteries. If this is the case, what type of error was made? So here our conclusion was that we failed to reject the null hypothesis. With that, it is possible that a type 2 error was made. We failed to reject the null hypothesis, even though it actually is true that the batteries do have a shorter lifespan. That would be the error, that we made that conclusion even though it was actually true that the batteries had a shorter lifespan. Designing an experiment. Confounding variables. In experiments, it is important to consider the potential confounding variables, which could influence how we must interpret the causal relationship. A confounding variable is a variable that has an effect on the response variable, but was not properly controlled for in the experiment. For example, suppose a student living in a dorm wanted to do an experiment to see if offering a free t-shirt would get more people to come to his social activism club. He put up large signs on the 3rd and 4th floors of his dorm advertising a free t-shirt and free pizza to those who attended the next meeting. He did not put up any signs on the 1st and 2nd floors. He found that more students from the 3rd and 4th did, in fact, attend the next meeting. After talking to a Statway student, he realized he could not conclude that offering a free t-shirt increased attendance because there were confounding variables in his experiment. Number 16, what are two potential confounding variables in his experiment? So he couldn't conclude that offering a free t-shirt increased attendance. So what else could have increased attendance? Well, one easy thing is, what else was he actually giving away? Free pizza. The other confounding variable could be where he was putting up these signs. He was just putting up signs on the third and fourth floors. He did not put up any signs on the first and second floors. So why did he notice that more students were coming from the third and fourth floors? Because he only put signs up on those floors. Researchers should attempt to control for such confounding variables by carefully designing their experiment. Number 17. How might the student have controlled for the two confounding variables that you noted in your answer for question 16? So first of all, instead of offering two incentives, t-shirt and pizza, he should have just offered one. And then instead of just favoring the third and fourth floors, he should have put signs on all floors.